And I think in the last lecture, we have looked at how actually a materials can conduct electricity and how we can define resistance. Okay. We also have looked into some different definitions and I think some standards, range value of conductors, semiconductors, and insulators. And further after this, we are going to look at how the effect of imperfection, temperature, deformation can affect the conductivity of the materials, and similarly for semiconductors. Okay, so for electrical conduction, I believe we have went through this maybe definition that one of the most important characteristic is of course it can actually transmit an electrical current. So conduction actually occurs when you have how to say current, and current is actually resulted from the flowing of electrons. Okay, so when you have a flow of electrons and everything, it will actually produce current, and when you have current that is moving, okay, or mobilized electron, then of course, at the end of the day, you're going to have conduction. All right. So we cannot run away with the basic concepts of Ohm's law, where potential is directly proportional to current and also resistance. Okay, and there's a few characteristics I think with regards to current flow. If you have a smaller cross-sectional, and also a longer length, so meaning that it will actually decrease the current flow. Okay. So what does it mean by smaller cross-sectional area? So imagine that if you have a very narrow wire, cylindrical wire, and a wider wire. So the area between these two, okay, is totally different. So you have an area 1, area A, and also area 2. So this one, of course, it will give a bigger area because it has a bigger radius or diameter. So the electrons can be easily flowing through the one that has, I think, bigger cross-sectional area. In the same time, if the length is shorter, so if the length is actually shorter, then it is also will give, I think, higher conductivity. Okay, shorter length will give higher conductivity. Longer length will give a lower conductivity due to, I think, higher resistivity. We've looked into this definition as well, how you can actually look into, how to say, the intrinsic resistivity, rho. So rho is actually equals to resistance multiplied with area over length. Okay. And we also have looked into conductivity. So things that you need to remember is conductivity, or sigma, is inversely proportional to resistivity. So if you have a higher resistance, okay, higher resistance, because resistance and resistivity is directly proportional. Okay, so if you have higher resistance, it will actually give a lower conductivity. Okay, and some basic things that you need to understand is that for conductivities, it has a classification. Conductors values, normally conductivity is larger than 10 to the power of 5 ohms over meter or Siemens. So we have a standard unit for conductivity, Siemens. Okay, or sometimes noted as S. S over area lah. Sometimes you as Siemens over centimeter square, Siemens over meters square, or whatsoever. Okay, semiconductors normally will have values in between. Okay, 10 power of 10 power of 5 to lower, 10 power of minus 6. So in between this, actually 10 power of minus 4, 10 power of minus 3, minus 2, and whatsoever will fall under semiconductors. And finally, if we have, I think, conductivity value that is in the range of 10 power of uh, minus 6 and below, for example, 10 power of minus 8, minus 10, then this can be categorized as insulators. Okay. And we also have looked into power. So what does it mean by power? It's actually produced when the current flow through a resistance. So this will give a power. Normally power unit is in watts. Okay. Right. And other things will be related with current density. So current density, what does it mean by current density? So current density, it means that current over surface area. Okay, and current density is also equals to the conductivity multiplied with voltage over length. Okay, so today we are going to look into a simpler example. Okay, example 1. An electric heater element is made of nichrome. So nichrome is actually an element that is made from nickel and also chromium. Okay, so nickel and chromium, you can actually check whether this one is actually isomorphous or not. Okay, you can check based on the Hume rotary rules. Please check through the physical properties, and you can actually understand whether it is actually isomorphous or non-isomorphous. Having resistivity equals, okay, to 100 power of times 10 power of minus 8 ohm meter. The diameter of the wire is 0.3 millimeters. Calculate the length of the wire required to get resistance of 30 ohms. Okay. So from here, actually, we know that the resistivity, rho, is actually equals to 100 times 10 power of minus 8. So we know that also rho is also equals to RA over L, isn't it? Okay. So the question actually asks for the resistance. It asks about R. So R is actually equals to rho multiply with L over area. So area you can actually calculate from the diameter of the wire. So A is actually equals to pi r square. Okay. So pi, the diameter is 0.3, divide by 2, and then after that you square it. Okay. And in the end of the day, you will get the value. So you can actually do the conversion even before. So you just convert millimeters to meters. I guess it's better to convert in meters because the unit given for the resistivity is ohm meter. So you know that this is in meter, this is actually in millimeters. So you can actually times power of -3 over here. So you will get area will be equals to 7.06 times 10 power of minus 8 meter square. Okay. And then after that, the the question actually asks about the not the resistor. No, dia nak tanya pasal length actually. It's my mistake. So you can delete this. Oops. Okay, so the question actually asks about the length. So if we actually reorganize back the question, it will be area, resistance, Silap. Uh, mhm. And then after you have done the substitution, okay, you will get the length. That is equals to 2.12 meters. So this is actually taken from, uh, of course, from this formula. Nampak tak yang ni? Okay. So what about the other examples? So the other examples, a current of 10 amperes is passed through a 1 millimeter diameter wire with a length of 1000 meters. Calculate the power loss if the wire is made of aluminium. Conductivity of aluminium sigma is equals to 3.77 times 10 power of 5. Okay. So over here, according to the formula, power P is equals to V multiplied with I and also equals to current square R. The resistance R is related to the physical dimension of the wire as well as the resistivity. The conductivity is inversely proportional to the resistivity. So therefore, okay, power, if you actually substitutes the whole thing together, okay, R is equals to this one. This one is actually taken from formula for conductivity. If you substitute here and A over here, then you will get power is equals to 4 times length multiply with current square over pi density square multiply with conductivity. Okay. Then if you I think put the values everything inside the formula, then you will get power is equals to 3.37 times 10 power of 5 watts. Okay. So if you have time, please try and see whether you get the same answer. So this one is actually before we end our lecture last week. Which one have the greater resistance? Which one will have a greater, resistance and lower conductivity? So over here, you will see that there's two rods. One having a smaller cross-sectional area and a longer length. The other one have a bigger cross-sectional area and a shorter length. So obviously, if you actually calculate what would be the resistance, okay, and you actually taking care of the formulas given to calculate resistance, then in the end of the day, you will get that it is actually around 8. Resistance is around 8 times. And meanwhile, for I think rod number 2, it is actually around 1/8 resistance as compared to R1. And obviously, this is actually smaller than this one. This is 8 and this one is actually 1/8. And obviously, we know that smaller resistance, okay, will have a higher conductivity, but greater resistance will give a low conductivity, right? So some comparison in terms of conductivity values. If you have a different materials like, for example, metal, ceramic, semiconductors and polymers, the conductivity values is roughly as this. Okay, metal normally will be very conducting, very much conducting, with the conductivity value is more than 10 power of 5. Ceramic is normally not conducting, Okay, because it's entirely inorganic, it doesn't have any mobilized electrons or whatsoever, then the value is quite low. Okay, that is why ceramics is normally used as insulators, sebagai penebat, for thermal, for electrical, and it is actually the best insulators. Okay, best insulators. Semiconductors, meanwhile, it is actually in the range, as I said, in between, like silicon, germanium, gallium, arsenic. So silicon is normally used in any semiconductors devices. If you heard about wafer, not wafer biscuit tu, okay, electrical wafer is normally made of silicon because it can actually store data or information. Meanwhile, for polymers, if it is entirely polymer, then it will be non-conducting, because polymer is a hyperbranch and a long chain structure. So it doesn't have any, I think, interaction or conduction side that it can give rise to conductivity values. But there's also a terms known as conducting polymer. Okay, so conductive polymer such as polyaniline, polypyrrole, okay, and if let's say that if you have blend, I think polymer electrolyte, for example, polymer electrolyte. So what does it mean? It means that you have polymer plus with salts, or dopant. Normally, conducting salt, lithium salts, sodium salts, then this polymer electrolyte can be conducting and normally used in most of devices, electrical devices. Okay, all right. So any question before we go to understanding conduction through electron energy band? Any questions so far? Okay, right. So this could be considered as one of the important part in electrical properties, explaining electron energy band. How actually one material can give conduction. As I said, it is actually due to the movement of electron. But when we say electron movement and whatsoever, it is not as simple as that. It depends on the types of material or elements that we are talking about. So each element have its own different electron number, proton number, mass, and whatsoever, orientation in terms of orbital state and whatsoever. So all this will give a different variation. That is why you have different values of conductivity, because some actually have a very low electron number. It can easily promoted, experience promotion from one orbital to another orbital. But if you have like more electron and with a more stable configuration, then the things will be different. Okay, so atoms form a solid, and this interaction is normally due to the valence electron interaction. And two quantum's mechanical effect that you have learned even during your high school, during your matriculation, during your STPM, during your A level. These two quantum mechanical effect that we have learned is basically according to the configuration. You have Heisenberg uncertainty principle, and you also have Pauli exclusion principle. Okay, Heisenberg's uncertainty principle, it says that constrain electrons to a small volume, which later on will give rise to their energy that calls promotion. Okay, Heisenberg says that each and every materials, it has very finite electron volumes. Okay, and what happened is that if it actually receives some external energy or some disturbance or some effect from outside, okay, the electrons tends to migrate from one orbiter to another orbiter. So this rise of energy is called promotion. Pauli exclusion principle. So if I ask you a very simple element, hydrogen, atom, hydrogen. What is actually the proton number and the electron number? Ini we just want to check your basic chemistry. Gui, King, Gui King what? Gui King Sheng. Are you there?
Yes, doctor.
Okay. All right. A very simple question. You have hydrogen atom. So what is actually the proton number or the electron number?
Proton number is 1.
Okay. Right. Electron number?
1.
Also 1. All right.
Yes.
If I ask you, what will be the Pauli exclusion configuration for hydrogen?
1s1.
Okay, very good. So you actually remember your basic chemistry. Okay, so this is actually what we're talking about. Okay, 1s1. Okay, so we know that it has a proton number of 1, electron number of 1. Okay, I think maybe during your high school, I think maybe Form 4 or Form 5, you learn about the, I think, electron configuration of 2, 8, 8, 2, something like that. Okay, so this is actually according to the period. So you have orbitals. We assume that one atom, like hydrogen, it has an orbital, so you have an electron outside. So this orbital can hold 2 electrons, for example. So that is why you have this configuration. But now we are not looking to this configuration anymore for, I think, a higher level. We are talking about, I think, Pauli exclusion principle, where you have the arrangement of electron follows and a configuration. Okay, so 1s1. Okay, so s orbital normally can holds or can have like or can occupy how many electrons? Ini saya nak tanya orang lain. Hafizah Adibah. Hafizah ada tak? Very simple question. Hafizah?
Yes, doctor.
Okay, so s orbital, how many electrons that it can occupy? This orbital can occupy.
S orbital.
Kacang ni. Kucing saya boleh jawab ni. Berapa s orbital? The lowest orbital. The lowest orbital normally dia tak banyak pun. Berapa?
2.
2. Jawab kena confident. 2. So s orbital 2. So apart from s orbital, what do we have? Hong Zili. P orbital. Okay, so p orbital, how many electrons that it can occupy? Sorry, again?
6.
6. Okay, right, 6. Right. And other than that, what kinds of, what would be the higher orbitals that we can have apart from S and P? Izzat Nazri. Izzat ada, Izzat? ada. Okey, Mardiana Zubir. Mardiana Zubir ada tak? Mardiana pun tak ada, tak bangun
Yes,
tidur.
doktor.
Ada. Okey, baru nak cakap tak bangun tidur lagi. Okey, Mardiana. Selain S and P orbital, ada orbital apa lagi?
D.
D orbital. Berapa banyak elektron yang boleh dimasukkan dalam orbital D?
8.
8?
Sekejap. Tak ingat.
Come on. Student kimia tak tahu, alamak. Okey, tak apalah. Dah mencuba 8 Agak-agak ada nombor lain tak nak diteka
10.
ataupun rasa 10. 10 D orbital can occupy 10 electron. Yang ni kena ingat. Because later on when we study about this energy band diagram, you have to know that each and every elements or atom have different or unique electron number, which later on will give a different orbitals occupation, different arrangement in orbitals, and it will actually give a different results in terms of conductivity. Alright. So, as a result, valence electrons, ni bila kita cakap, when we talk about valence electron, what does it mean by valence electron? Again, I just want to check your basic concept lah. Nick Muhammad apa ni?
Yes, doktor.
Okay. Apa yang dimaksudkan oleh valence electron? What does it mean by valence electron that you understand? Dah belajar sekolah menengah dulu. Semua. What does it mean?
Electron at the what we call it?
Highest what? Highest
What is
orbital.
that? Highest orbital.
Okay. So we say that the electron that will be located in the highest level of orbital will be the valence electron. And this valence electron is normally related with any sort of interaction. If it want to form bonding, for example, ionic bonding, covalent bonding, you learn this. This electron normally in valence band that will actually have experienced the promotion, transfer, and whatsoever. Okay? All right. So, again, valence electrons form wide electron energy band in a solid by splitting a distinct atomic state into a series of a closely spaced electron state, which we call it as electron energy band. Okay, so bands separated by a gap where electron cannot exist. Okay, so we have a so-called macam kat sini, I'm not sure whether you can see it. You have atomic orbitals, and then you have molecular orbitals. So this molecular orbital is normally can be referred as maybe valence orbital, and you have higher energy state, which actually a higher band. This is actually vacant, kosong, dia tak ada apa-apa. Electrons from the valence band can be promoted to the conduction band if there is any source lah, ada apa tu energy from outside, external energy that goes into the or absorbed to the atom, and then promotion can occur, okay, and goes into this conduction band, right? So this band, the conduction band and also the valence band, are separated with a gap. Ni ada gap ni, okay, and this gap is normally known to be electron gap. Okay, all right. So Fermi energy. Okay, Fermi energy is the minimum energy required to surpass from valence band to conduction band. Okay, it is normally highest field state at 0 Kelvin. Conduction band, okay, partially filled or empty band, and we have valence band, highest partially or completely filled band. So yang ni yang kita cakap ni. Conduction band. This is actually the one located at the higher state. This depend. Okay. It can be partially filled or empty. Empty kalau tak ada apa-apa lah. But if there is any promotion, then it can be partially filled or no. Okay. So valence band. Valence band is the where the valence electron is located at. Okay. So highest partially or completely filled band. Right. So in energy band structures, okay, I think as we know that we have like 1s, 2s, 2s, 3s, 1p, 2p, 3p. All these are actually depend on apa tu, the period, dia punya color. Okay, and we know that for s, I think orbital, it can actually have 2 electrons maximum. Okay, p orbital have 6 electron maximum. D orbital have 10 electron maximum. Okay, and due to the arrangement of Pauli exclusion, I think principle that we have talking about just now, it can be translated into the energy band structure. Okay, so how actually you see this? So this actually tells you that lower configuration like 1s will be located at the low part, and the higher band, or so-called the one that considered as the valence electron or valence band, will be located at the higher energy, 3p for example. Then you will see that it will be arranged in this kind of order. Okay. So first, we are going to understand how the energy band structures of insulator and also semiconductors. Okay. Semiconductors and insulators, the valence band is filled and no more electron can be added. So this actually Pauli's principle. It means that, okay, whenever we arrange it into this configuration, Pauli's principle of the configuration, the valence band is normally filled. Katakanlah the valence orbital is S. So it has 2s, maybe 3s2. Then it's already been filled. So no more electron can be added. Okay, as I said, this actually depends on number of electron that the atoms have lah. Electrical conduction requires electron gain energy in electric field. Okay, conduction can only occur if the atom or the element receive energy from outside, from electrical field. Katakanlah you ada satu material, getah for example, rubber, and then after that, if you didn't actually put anything, it just remain as rubber. But if you connect the rubber with a supply, katakanlah you have a battery, you have 2 terminals of battery and you clip into this rubber. So what happens is that it will experience something because you have a energy from external that interrupt the system. Okay, so not possible in this material. It has a forbidden gap. Probability, okay, an electron reaches the conduction band is exponent minus Eg. Eg is actually gap energy, band gap energy over 2kT. Okay, and T is actually the temperature in Kelvin. K is actually the factor values. Okay. Semiconductors and insulators, electron must jump across the band gap into conduction band to find conducting state above Fermi energy. As I said, Fermi energy is the minimum number of energy required in order to make it, I think, conductive. So awal-awal mungkin kita nampak, okay, all these are actually been failed. When it actually receive external energy, it need to overcome minimum amount of energy so that the electron can be jump to conduction band. Okay. So what will be the minimum Fermi energy required for semiconductors? Normally for semiconductors, the band gap is very narrow, rapat. And the Fermi energy is less than 2 eV. 2 eV is actually the unit for energy. Okay. Meanwhile, for insulators, the band gap normally have a wider space lah. And the Fermi energy is greater than 2 eV. So this why it is almost impossible for insulator to have conductivity because the energy level is always higher. Okay. Alright. So energy is needed in order to have promotion. It's either via heating or radiation. Okay. So radiation can cause some instability to the electron. Katakanlah you have one materials, it's already stable, okay, it has a field valence band, and you actually expose it with some radicals, okay, some radiation, H nu, for example, from sunlight or whatsoever. So the electron will start to feel unstable and it want to go out. Ada benda kacau lah. So make it feel uncomfortable and want to move from its current location. So that is why it will actually experience promotion, and finally it goes temporary. Temporary, it will goes into the conduction band. So what will be the difference between insulator and semiconductors? As simple as if you look into the band gap. Semiconductors electron reach conduction band at room temperature. Okay. Meanwhile, for insulator, it is not. Okay. An electron promoted to conduction band leave a hole, a positive charge in the valence band. So it also participates in conduction. So dekat sini, okay, for semiconductors, after the energy is being received through heating or radiation, the electron will promote. Okay, katakanlah dekat sini you ada 2 elektron. Have 2 electrons. Okay, so one, after you have transferred it, okay, so what happen is that this one will have 1 and this one will have 1, but it has a hole, H. Okay, so this hole is actually a positive charge. Ingat tak kalau kata I think in any theories, if let's say that it is positive charge, then it means that it is have a unoccupied electrons because dia dah pergi apa tu transfer or donate, or for example lah. Right. So another I think explanation in terms of insulator and semiconductors, this I think with regards to the valence band. So for insulator, it has a wide band gap, more than 2 eV Fermi energy, okay, or EG, gap energy. A few electrons will be excited across the band gap, okay, but end up it didn't manage to arrive at the conduction band because of the gap is very huge. Nampak tak dekat arrow kat sini? You see an arrow over here. It still actually experience promotion, but it cannot overcome that level of energy and it will return back into valence band. So that is why insulator will never give any conduction. Meanwhile, for semiconductors, it has a very narrow band gap, narrow. E.g., the gap energy is less than 2 eV. So the electron can easily excited across the band gap. So electrons from the valence band, it can actually cross through the band gap and it can goes into the empty conduction band. And later it will leave a hole. Lubang. Right. So how about conductive material? For example, metals. Metals have a highest occupied band, which could be partially filled or overlap. For metals, empty energy states are adjacent to filled states. Conduction will occur by promoting electrons into conducting states, starting right above Fermi level. Okay? Energy provided by an electric field is sufficient to excite many electrons into conducting states. Okay? So, in this case, we also have a term known as thermal energy. So, thermal energy, it means that you have received the energy in terms of heating. Okay? It will excite the electrons into the empty higher energy states. Okay? So, thermal energy, okay, will give an influence to the valence band. Okay, so this is actually the valence band. Okay, all right, and this is actually the conduction band. When you heat this material, so what happens is that the electron can excite into higher empty energy states. There's two types of band structure for metals. One, partially filled band, and second, empty band that overlaps with filled band. You can have partially filled band and also overlap filled band. Yang ni, how can we know that it is actually partially filled or overlapping filled band? We have to look into the examples. And the examples is actually related with the types of atoms or element that we are talking about. So this here, I think I put an examples of copper and also magnesium. Copper. So what would be the electron configuration of copper? Copper berapa dia punya ni? I think the proton number, the atomic number or the proton number. Copper. Siapa tahu? Copper is actually 29. 29. Yeah. Copper. 29. Yes. Magnesium. Magnesium siapa tahu? Berapa? 12. Okay. Alright. So if you write the electron configuration, okay, in the end of the day, you will get the valence band, the outer band. You will have a field 3D10, 3D10 and 4S1. So what does it mean by 4S1? You see, partially filled. You have one filled band. This is actually for D orbital, and partially filled. This is actually for 4S1. Macam kita cakap tadi, I think when we said how many electrons that S orbital can occupy, we know that S 2, okay, P 6, D 10. Okay, so over here, obviously we see that the valence electron is actually 4s1. It is partially filled. It is not completely filled. Okay, D orbital is fully filled, so that is why it is located below. All right. And how about magnesium? So magnesium, okay, you'll see here it is actually having a filled band. It has 2p6 and then 3s2. Both are actually filled. Okay? All right. So that is why whenever you have elements or atoms that have a field Okay, valence band. Metals, when we talk about metals, metals that has field band, then this can be seen that, or can be explained that it will form overlapping band, energy bands. Meanwhile, if you have a metal that has partially filled band, then it will actually follow this energy band diagram. So have to remember, for metals or conducting material, you have two different I think energy bands. You have a partially filled and also overlapping. Overlapping, it means that you have a filled band, and partial, of course, it means that it has partially filled valence band. Okay. All right. Maybe last few slides before we end our lecture today. So the energy band and structure, relation to atomic bonding, metals, insulator, and semiconductor. This is actually as a summary. So we know that for metals, it can actually have, I think, a field, or we say as overlapping, or partial field. Okay. Valence electron forms electron gas. For semiconductors, okay, semiconductors, this is actually insulator lah. Insulators and semiconductors. Energy gap, EG, is greater than 2 eV. Meanwhile, for semiconductor, it is less than, EG is less than 2 eV. Right. Insulators, valence electron tightly bound to or share with individual atoms. Ionic plus covalent bonding. Okay. Meanwhile, for semiconductors, mostly it is a covalent bonding. Another, I think, summary, okay, that differentiate between conductors, semiconductors, and insulators. Okay, for conductors or metals, it could be partially filled or fully filled. For semiconductors, okay, you will have energy gap that is more than 2 eV and sometimes going up to 4 eV. Okay, and for semiconductors, it can be less than 4 eV or less than 2 eV. Okay, so in some questions during exam, you are required to explain the conductivity or the conduction of different materials. For example, metals, conductors, semiconductor as insulators. So in order to explain, you have to explain by means of energy band structure. So what does it mean by partial field and overlapping field for conductors? Meanwhile, for semiconductors and insulator, why insulators cannot form any conduction? Because of the energy band is wider. And then for semiconductors, it can form conduction because of a narrow band gap. Right? So all this, I guess, maybe need to be understand, and with that, maybe you can able to explain those kind of questions. Electromobility, I think maybe we will go through this tomorrow. So before that, is there any question, anything that you would like to ask before I end my lecture? All right, so I will stay back for a few minutes if there is any question, private question. But if you don't have any questions, so I would like to join the class. Thank you very much for your kind attention, and hopefully to see you tomorrow. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.